Good morning or good evening to all. We are from Group 4 and going to talk about the topic of transfer function and plot graph. We are discussing the transfer function and plot graph based on the task given, which are question D and question H. Next, may I introduce our group members? They are Teo Yin Chai, Lo Meng Yao, and No Karina Shafika binti Muhammad Fauzi, and me, Teng Bao Yun. From the content page, we get to know that the assignment was being distributed into 4 parts, which are introduction, methodology, analysis and results, discussion, and conclusion. I responsibility to present the introduction part and video editing. Then the methodology and analysis result will be performed by Teo Yin Chai, and the discussion part will be taken over by Lo Meng Yao. Lastly, the conclusion part belongs to Kai. Okay, so what is the transfer function? Transfer function is a useful tool for finding the frequency response of a circuit. It is dependent ratio of phasor output to input, which defined as ratio of the Laplace, Laplace transforms of the output to the input. After that, we can refer to the diagram below. It shows the poles of the transfer function are the values that make the denominator of the transfer function zero, and they indicate the natural frequencies of the system, whereas the zero are the values that make the numerator zero, and they indicate the frequency at which the system output is zero. Afterwards, the main point of the topic is converting the transfer function into plot graph, which are magnitude plot graph and phase plot graph. So in the addition, the transfer function can also be divided into 4 types. They are voltage gain, current gain, transfer impedance, and transfer admittance. The gain is essentially a measure of application and is defined as the ratio of output quantity to the input quantity. The current gain and the voltage gain are dimensionless quantities and thus have no units because they represent the ratio of two quantities that have same unit. Then the transfer impedance is measure of how much voltage at output is produced in response to current applied at input. Therefore, the unit of transfer impedance is ohm. In contrast, the transfer admittance is measure of how much current at output is produced in response to voltage applied at another port input. Hence, the unit of transfer admittance is Siemens. Thank you.
Hello, I'm Yin Chai. I would like to present how to draw the magnitude and phase plot from transfer function. So this table as a reference to draw the plot, and the second column is gain, and the last column is phase. So let's begin to draw the magnitude plot graph. So firstly, our transfer function equation is 15 j omega over j omega plus 4 times j omega plus 10 power of 2. So when we simplify the transfer function equation, it will become 0.125 j omega over 4 plus 1 times j omega over 10 plus 1 power of 2. So first factor we want to draw is gain. So we can use the equation which 20 log k. So which our k is 0.125. So we get negative 18 dB. So we'll draw a straight line at negative 18 dB. So next, second factor to draw is j omega. So first we will plot a point at 1 radian per second and 0 dB. After that, we will increase 20 dB and 1 decade, which at 10 radian per second as second point. And we will draw a line between these 2 points. So this orange line is as j omega. So the third vector we draw is symbol pole, which 1 over 1 plus j omega over 10 power of 2. So we'll draw a straight line from 0.1 radian per second to 10 radian per second and 0 dB. So from the equation, we notice that it's got a power of 2. So we will plot at negative 40 dB and 1 decade, which at 100 radian per second, and draw a line downwards. So the purple color is symbol pole as 10 radian per second. And fourth factor we draw is symbol pole, which 1 over 1 plus j omega over 4 and power of 1. So we draw a straight line from 0.1 radian per second to 4 radian per second, and at 0 dB, so at at 0 dB. So we will plot at negative 20 dB and 1 decade, which at 40 radian per second as one point, and plot the second point at negative 40 dB 1 decade and at 400 radian per second. So we draw a line downward between these 2 points. So the green color is symbol pole at 4 radian per second. After we finish draw the all factor, we need to draw the resultant line. So first we can draw some dotted line at 0.1 radian per second, 4 radian per second, and 10 radian per second. It can help us easily to draw the graph. So we can find the magnitude at all factor at 0.1 radian per second, which can K at negative 18 dB, J omega is negative 20 dB, and the two symbol pole are at 0 dB. So we add on them is equal negative 38 dB, which is this one is a first point. So second point at 4 radian per second, gain is negative 18, j omega is 12 dB, symbol pole is at symbol pole at 4 radian per second and 10 radian per second are 0 dB. So add all of them is negative 6 dB. And the third point is at 10 radian per second. Also, when we add on them all the factor at at 10 radian per second, also negative 6 dB. So the last point we can draw at 100 radian per second, because we can see all the factor at there. So the gain is negative 18 dB, j omega is 40 dB, symbol pole at 4 radians per second is negative 28 dB, and symbol pole at 10 radian per second is negative 40 dB. So add on them, all of them is negative 46 dB. So after we can draw a line to connect the every point together. So the black color is a resultant plot. So this is the method how to draw the magnitude plot. Next, I will talk about how to draw the phase plot graph. So first, the first factor is gain k, so we can refer the table as first column. So we just draw a straight line at 0 degree, which is blue color one. So second factor is j omega. So from the table we can see it's draw a straight line at 90 degree. So which is the orange color at the graph. So the third factor is symbol pole at 4 radian per second. So refer to the table P, which is 4 radians per second. So draw a line at 0 degree from 0.1 radian per second to which P divided by 10, so it's 4 divided by 10, so equal to 0.4 radian per second. So going downward at negative degree and 1 decade at 10 times P, so which P is 4, so it's 10 times 4, so it's 40 radian per second, and draw a straight line until the end at negative 90 degree. So the fourth factor also a symbol pole, which is at 10 radian per second. So same as the third one, which from 0.1 radian per second to 1 radians per second at 0 degree, and it is because of power of 2, so we need to draw at negative 118 degree and 1 decade, which at 100 radians per second, and after it's draw a straight line until until the end at negative 18 degree. So after that, we will draw the resultant broad plot. So it's at 0.1 radian per second. We will add on there and we'll draw at 90 degree. And when at 0.4 radian per second, also draw at also draw at 90 degree. So when at 1 radian per second, plot at a point at 72 degree. When at 40 radian per second, we'll plot a point at negative 144 degree. When at 100 radian per second, when at 100 radian per second, we'll plot a point at negative 118 degree. So when at 100,000 radian per second, we will plot a point at negative 118 degree, and we will connect all the points together, and red color is the resultant phase plot. And this is how we draw the phase plot. That's all for me. Thank you.
Hello everyone, my name is Lo Minghao. First of all, I would like to thank my teammate Yun Chai for the explanation from transfer function to block plot just now. Now, I would like to explain on how to change from block plot to transfer function. From the graph presented, we know that the gain is 14 dB. The formula to get the gain is 20 log k. In order to find the value of k, we use 10 power of 14 divided by 20. The value of k that we get is 100. Secondly, we notice that the graph is going downward with a negative 20 dB per decade. From this, we know that it's a simple pole structure. The formula to get this simple pole is 1 divided by j omega per 100 plus 1. Thirdly, the graph is maintained constant at 20 dB, which means that there is a simple zero structure after the simple pole. The formula to get the simple zero structure is 1 plus j omega per 1000. After finish analyzing the structure, we should combine all of the structure in one equation. The equation is h omega equals to 100 multiplied by 1 plus j omega per 1000 divided by 1 plus j omega per 100. Until this step is not finished yet, we need to simplify the equation. For the simple zero equation, we need to multiply by 1000 divided by 1000 since the value of z is 1000. While for the simple pole equation, we need to multiply by 100 divided by 100 since the value of p is 100. After finish this step, we should simplify it, and the final answer is 10 multiplied by j omega plus 1000 divided by j omega plus 100. Next, I would like to explain about the discussion. Transfer function, which is h omega, is a frequency dependent ratio and also can be defined as voltage output divided by voltage input. Transfer function can turn into two types of block plot, which is magnitude block plot and phase block plot. For the magnitude block plots, it is in decibel form, while for the phase block plot, it is in degrees form. There are some precautions in this assignment. First is, before drawing the block plot, we need to convert the transfer function into standard form. For the magnitude block plot, for each pole, the slope decreased by 20 dB per decade, while for each zero, the slope increased by 20 dB per decade. For the phase block plot, the transfer function for a pole or zero starts 1 decade before and ends with 1 decade after the corner frequency, changing by plus minus 45 degrees per decade. Thirdly, if there is a quadratic equation, we should draw up to 14 dB per decade. That's all for me, and now I would like to pass the presentation to my next teammates.
So my name is Nakarina Shafika Bente Mawat Fauzin. Now I will present the conclusion. So the first conclusion is the importance of transfer function. The transfer function is a cornerstone of control system and signal processing, providing essential insight and tools for system characterization. stability analysis, frequency response evolution, control design, predictive modeling, and system interconnection. It transforms complex dynamic equations into manageable form, facilitating efficient and effective analysis and design. By leveraging transfer function, engineers can ensure that systems perform reliably and meet desired specifications across a wide range of applications. So next is conclusion for importance of managed and phase bot plot. Managed bot plot show how the amplitude of the output signal varies with frequency. This helps in identifying frequency where the system amplifies or attenuates signals. While phase bot plots show how the phase of the output signal shift relative to the input signal across different frequencies. This is crucial for understanding the timing and synchronization aspect of the system response. So next conclusion is how to get more precise of bot plot graph. So to obtain a more precise bot plot graph by focus on high quality data collection, accurate system modeling, fine frequency resolution, advanced numerical method, data smoothing, and using high plotting tools. Calibration and validation are also crucial to ensure the accuracy and reliability of bot plots. By following this step, it can achieve a detailed and accurate representation of system frequency response. Next is conclusion for bot plot to transfer function. So by converting a bot plot to transfer function involve extracting gain and phase information, representing it as complex number, and constructing the transfer function equation using components like gain, poles, and zeros. Normalization may be needed for standard form. This process depends understanding and facilitate analysis using transfer function technique. Last one is transfer function to bot plot. So, converting a transfer function to bot plot involves analyzing its poles and zeros, determining its behavior across different frequency range, and plotting its magnitude and phase response. This graphical representation offers valuable insight into the system frequency response characteristic, aiding engineers and research in analyzing and designing systems with specific frequency response.